is Math Jazz from Almost Cool. This is Livestream number 4, not 2. And I have a list of problems to solve today. I also am awaiting all of your problems. If you have any problems that you'd like to send to me, you can send them to mathjazz9@gmail.com. I have in the chat here Mark Lund. Hi, Mark. It's good to see that you're watching. And if you have any math questions, Mark, feel free to email them to me. So, I will now take the main title off the screen. That's odd. I'm sure I programmed that correctly. Oh, do these count as text cells? That's unfortunate. Anyway. So, email your questions. I'll leave this at the top of the screen for your future reference. And without any further ado, problem 1. Okay. Oh. Forgot to execute these cells. There we go. Find the derivative of 2 times the cosine of x squared plus 1. So, this is a chain rule problem. The coefficient on our function is 2, and that can be just brought out in front. So, the 2 gets left alone. The derivative of cosine is negative sine, and we have to plug in our inside function, which is x squared plus 1. And then we have to multiply by the derivative of the inside function, which is 2x. So, we're left with negative 4x times the sine of x squared plus 1. So that's an easy problem. Let's see if problem 2 is any better. There we go. So, show that among all right triangles of hypotenuse h, the right isosceles triangle has the greatest area. I might have spelled isosceles wrong. It doesn't matter. We know what it means. It means to have the 2 legs of the right triangle having equal length. So, how do we prove this? Well, we know that the 2 sides of the triangle are, well, we'll call them x and y, and we know that the squares of each of these have to equal the square of the hypotenuse. Sorry. There we go. We know this. And we know h is a constant. So, with this, we can solve for y squared. We get y squared equals h squared minus x squared. And in fact, we can solve for y by taking the square root of both sides. There we go. So we have our relationship between the 2 sides and the hypotenuse. We've solved in terms of y. We note that the area of a right triangle is that 1/2 times the length of the first leg times the length of the second leg. So that'll be 1/2 xy. So area equals xy over 2, but that is equal to this x, and then we substitute in for y, so we get the square root of h squared minus x squared. Now we have our equation for area. Area equals x times the square root of h squared minus x squared. Okay. We take the derivative of both sides, because it gives us a prime is equal to, and we use the product rule here. So we have the derivative of the first function, which is 1, times the second function, which is square root of h squared minus x squared, plus the first function x times the square root, times the derivative of the second function, which is a chain rule problem. So the outside function is the square root function, and that'll be 2 times the square root of x, but we plug in our inside function, which is h squared minus x squared, and then we multiply by the derivative of our inside function. The inside function is h squared minus x squared, so its derivative is negative 2x. And that'll go on the top here, the top of our fraction. If you need more time to take these derivatives, feel free to pause the video and just review or check to make sure I'm doing this correctly. There's an error in last week's live stream that I didn't catch for a few minutes. Anyway, so this is our derivative. Notice that Mathematica has automatically canceled the 2 in the numerator with the 1 in the denominator for us, and that's great. We also want to set the derivative equal to 0. Because, of course, we're trying to maximize this area, which means finding a critical point of the equation. And so we set this equal to 0, and we try to solve for x. So I'm going to move the negative x squared over the square root of h squared minus x squared to the other side of the equation. Like so. I'll multiply by the denominator of the fraction so that I can get rid of the fraction. And that leaves me with something that looks like this. I add x squared to both sides. And I divide by 2. And I take the square root. Like so. So this gives me x, which is the length of one of the legs of the triangle. So let's call it this leg. I can use this number to figure out what the length of this leg should have to be, because if this is my x leg, then this is my y leg, and here is the equation that relates the two. So we'll go back to that. So we have x squared plus y squared equals h squared, which means that we have h squared, when we substitute in for x, over 2 plus y squared is equal to h squared. This will simplify to be y squared equals h squared over 2, which leads us to conclude that y is equal to h over the square root of 2. So, like so. Now, since this was also the value of x, that means that our triangle is an isosceles triangle, because two of the three sides have the same length, which is the definition of an isosceles triangle. And that proves what we set out to prove, so we can go on to problem 3 now. Show that among all rectangles of perimeter P, the square has the greatest area. I'll just reuse some of these math form boxes. So we know that the perimeter of a rectangle is equal to 2 times the length plus 2 times the width. We know also that the area of the rectangle is equal to the length times the width. And substituting, or first we'll solve for, let's say L. L is equal to the perimeter minus 2w, all of that divided by 2. If we substitute that into our equation for the area, we get the area is equal to w times p minus 2w over 2. We'll execute these code. Okay, so now we have area as a function of w, which means we can take a derivative. The area is equal to, we can multiply through or use the product rule. I'm going to multiply through. So let's do that. We have WP minus, well, WP over 2 minus W squared. There we go. So now if I take the derivative, I get P over 2 minus 2W. And we want to set that equal to 0. Notice that I didn't take the derivative of P. That's because P is a constant. We said for fixed perimeter. So that's why we treat P like a constant. All rectangles of perimeter P. Maybe I should explicitly say a fixed perimeter P, but that's understood that P is a constant for this problem. Anyway, so at this point we solve for W, that's our variable. And we're going to get that W is equal to P over 4, which is great. We plug this into our equation for L. Remember our equation for L up here. And we plug in our value of W. Oh wait, there we go. There we go. So that simplifies to L equals P over 4, but that's the same value as W. W is P over 4, so that means that we have a square. So of all rectangles whose perimeter adds up to P, the one that has the largest area is the square. That's pretty cool to know. Let's check to see if we have any questions emailed to us. It does not appear that we have any emailed to us. Let's check Facebook, see if there are any messaged to us. That doesn't look like there are any there either. So we'll go back to the regularly scheduled questions. Problem 4, I think. Find the dimensions of the 1-liter cylindrical can that has minimum surface area. So I have here a nice can. This can has, we'll call it a height of h. That's the distance from this face of the can over to this face of the can. And it has a radius that we'll call r. Let me see if I can pull the face over here. I know I had it over here a moment ago. There we go. So the radius of this circle here is r. Okay, so the dimensions of the 1-liter cylindrical can that has minimum surface area. So the volume of a can is equal to pi times the radius squared times the height. Like so. And we know that this volume has to equal 1 liter. The surface area of a can is going to be, well, we have a circle on this side and a circle on the other side. I don't know if I can get it to face us. It's an obstinate little cylinder. Anyway, so the area of each of those circles is pi r squared. So since there are 2 of them, we have 2 pi r squared as the area of the top and bottom of the can. The side of the can we can think of as just a rolled up rectangle, where the height of the rectangle is the height of the cylinder, and the width of the rectangle is the distance around the circle that makes up the face, the top of the can, or the bottom of the can. So that means that this area here will be the height times the distance around that circle, which is 2 pi r. I'm going to put the 2 pi out here, and the r, like so. So volume equals pi h r squared. Area equals 2 pi h r plus 2 pi r squared. Now we can solve for h in the volume equation. I don't know where this... Let's get rid of this one. We can solve for h in the volume equation, and then we'll plug it into the area equation. So we get that h is equal to 1 is the volume divided by pi times r squared. We substitute that into the area equation. Here's our area equation. That goes right here. And Mathematica has already simplified the r here with one of the r's down there, and the pi on the top of the fraction with the pi down here. Mathematica is really nice like that. So we have this, and we want to take its derivative. So that's going to be a prime is equal to 4 pi r minus 2 over r squared. And we want to set this equal to 0. So that means that we'll get 4 pi r is equal to 2 over r squared. Like so. And we cross multiply. That gives us r cubed is equal to, looks like 1 divided by 2 pi. Let's make sure I canceled that correctly. Yeah, there's going to be a pi in the denominator. 2 here will cancel with a 2 there. This looks good. So we take the cube root of both sides. R is equal to the cube root, let's see, 1 over 2 pi, and I think is that how it works? Or is that how it works? Nope. I forget how to do cube roots with Mathematica. That's okay. We have an alternative solution. Now this is our radius. We can plug this into our equation for the height here to get the dimension of the can. So let's do that. We'll plug, well, copy this down. And we will plug r into the equation. And this is our answer. That's not what I think the answer is. I think the 2 should be in the denominator. Oh, sorry. Taking the reciprocal here. Okay, so we have Mathematica simplified this for us from this form to this form. The 2 is in the denominator of r is in the denominator of h, so the 2 came into the numerator. Okay, so that is, these are the dimensions. We were asked to find the dimensions. If we were asked to find the area, we could plug these into our surface area equation, which is here, or we didn't really need to solve for h. We could just plug r directly into our surface area equation here. Pay attention to what they ask you on your exams, because sometimes they ask for the area and sometimes they ask for dimensions. Anyway, let's move on to problem 5. Show that among all rectangles of area A, the square has the least perimeter. Now, in our previous question, we had a fixed perimeter and needed to find the greatest area. With this problem, we have a fixed area and we want to find the least perimeter. So we're going to call this length of the rectangle, the horizontal side of the rectangle, we'll call it the length, and we'll call the vertical side of the rectangle, we'll call it the height. Or we can call it the width. We'll call it the width, just so that we can keep with the L and W thing. So the area is equal to the length times the width. Mathematica is remembering that the W, I accidentally assigned it a value. So maybe we should go to length times height, since height doesn't accidentally have a value. The perimeter is equal to 2 times the length plus 2 times the height. And if we solve the area equation for length, we get that the length is equal to the area divided by the height. So that means that we can plug the length into the perimeter equation, and we get 2 times the area over the height plus 2 times the height is equal to the perimeter. And we will take these cells and execute them like so. I did not mean to assign p a value. So p is equal to this expression here. When we take the derivative, we get p prime is equal to negative 2a over h squared plus 2. We also want to set this equal to 0, because that'll tell us where our minimum is occurring. So Mathematica is, I accidentally assigned p a value in this statement, so now p will always look like this to Mathematica. And I don't, well, maybe we can take some time to just quit the kernel for a second to undo that. Then we execute the code on our code page here and down here. And then we move back to our first page. There we go. Oh, I just did it again. Do that one more time, sorry. Evaluation, quit kernel, yes. Execute code, execute our other code, back to first page, and then, hey look, it works. Okay. So our derivative of p is equal to 2 minus 2a over h squared. We solve for h squared. So that gives us, well, we'll subtract this negative 2a over h squared to the other side. That'll give us 2 is equal to 2a over h squared. And the 2's will cancel. And so we multiply by the denominators. We get h squared equals a. We take the square root of both sides, and we get h is equal to the square root of a, like so. We will now plug this h equals square root of a into our L equation. So we get that L is equal to the square root of a over a over the square root of a is a over h. H is the square root of a, so a over the square root of a, which will be the square root of a. So L is equal to the square root of a. Since L and h equal each other, that means that we have a square. Since the length and the height of the rectangle are equal, that's the definition of a square. Okay, so here is problem 6. If the top and bottom of a cylindrical can cost 1 cent per square centimeter to make, and the wall of the can costs 2 cents per square centimeter to make, find the dimensions of the 1 liter cylindrical can that has minimum cost. So, this is a lot like our cylinder problem. A little different, but a lot like it. So, we'll write up a cost equation. So the cost is equal to, well, the area of the top and bottom are going to be 2 pi r squared, because each circle is going to be pi r squared, and there are 2 of them. But then we have to remember that it costs 1 cent for the top and the bottom. So we're going to multiply this by 1 cent. I'm going to leave this in cents. We can convert into dollars later if we choose to. But I'm going to leave this in cents. And then the area of the wall of the can is, like before, the height of the can times the distance around the circle that makes up the base or the top of the can. So that's going to be 2 pi r, that's the distance around the can, times h, but then times 2 cents. So 2 times 2 is 4. I could have placed this in dollars. That would have been fine. But if I did that, I would have to make sure that both terms are in dollars, because you can't add non-like units without converting. So if I had one of these in cents and the other in dollars, I would have to convert one into the other before I add. So here's my cost equation. Let me get rid of these. Here we go. Here's the cost equation. I know that the can has to be 1 liter. So that means that our volume is 1, and volume is equal to pi r squared h for a cylinder. That is, it's the area of the circle that makes the base times the height of the can. But that also means that our height is equal to 1 over pi r squared. And that helps us to substitute into the original equation so that we can get the original equation in terms of the radius only. So here's our calculations thus far. This is the cost of a can. This is the volume of a can with 1 liter plugged in for our volume. We have to make sure this is in square centimeters and our equations are in centimeters. So that's good. Oh wait. I may have done... Yeah, to be in square centimeters, this has to be 1,000 square centimeters is a liter. And that should be done on the other question too. When we found the volume of a cylindrical can that minimized surface area, we found the one for a 1 cubic centimeter can, not a 1 liter can. We didn't convert units properly. However, that was the dimensions for the smallest 1 cubic centimeter can, which is a really tiny little can. I bet it looks adorable. Let's make this 1,000. And that means that this is 1,000 over pi r squared. And this is also 1,000 over pi r squared. There we go. I will delete these. So from here, we want to take the derivative. So we get that C prime is equal to 4 pi r minus 4,000 over r squared. And we want to set this equal to 0. So from here, we will solve for r. That means we will move this 4,000 r squared to the other side, and we will multiply both sides by r squared to get rid of the denominator. That leaves us with 4 pi r cubed is equal to 4,000. We divide both sides by 1,000. Sorry, by 4. And by pi. And we take the cube root of both sides. Like so. This gives us the radius that minimizes the cost of the can. Now, we look back at our original equation, and we want to find the dimensions. We'll also find the cost because we can do that. But we were only asked to find the dimensions, and this is r. Plugging this into our equation for h here gives us the dimensions. Oh, that's cool. Apparently we get some really neat cancellation going so that the height and the radius are the same value. And for fun, let's plug this into the cost equation. So we take our R value, plug it in here, and here, and here. So this is the cost of the can. That seems like a fairly expensive can. But then again, we remember that this was a 1 cent per square centimeter for the top. And the top is apparently, well, whatever this number is. So pi r squared gives us 150 almost square centimeters for the top. So that's $1.46 for the top, another $1.46 for the bottom, and then the cost of the wall. So this is quite the can. Let's see what the total cost is in dollars and cents. So this is an $8 can. $8.79. That's pretty expensive can. I don't know what it holds, but it must be something that's hazardous. Needs to be protected, or needs to protect, the can needs to protect people from whatever's inside of it, as the can is very expensive. It's not like a can of water or soda or something. Okay, so this is the end of that list of problems. Let's see if we have any others. Okay, I think that I can pull up one here. Let's do a U substitution problem. This will be the first integral problem that we do on this live stream. Oh, where'd it go? Ah, here we are. Let's copy a text cell. What we really want is a math form cell. Here we go. Let's do the integral we have 3t over t squared plus 4. And we're going to integrate on t from 1 to 2. Oh, this decided to solve it for us. This will be the answer. But let's, okay, maybe if I just write out the fraction. There we go. We're integrating this from 1 to 2. So, the first thing we're going to do is we're going to let u equal t squared plus 4. Okay, so from here, after we let u equal t squared plus 4, we find the derivative of u, or u prime is equal to 2t t prime, or I guess du is equal to 2t dt. The t should be on the other side. Anyway, so from here, we can substitute. So we have in the numerator here we have this. Let's put a dt in the top. 3t dt. Oh, if I don't put the space there. Okay, so we have 3t dt. We know that du equals 2t dt, but we need a 3t dt to balance the equation. So we can multiply by 3 halves on each side, and that will balance the equation. The 2's will cancel. I get 3t dt on one side and 3 halves du on the other. And we can now substitute into our integral, which next week I will promise to have integral signs that I can do on Mathematica. But for now, we'll just have to imagine a nice, beautiful integral sign right in front of this fraction. So we substitute, and we get 3 du over 2 u, and that's it. The denominator was u, and the top was 3 halves du. So we get this. Oh, we need to put parentheses here. There we go. Now the integral of du over u is the natural log. So the constant gets pulled out in front. And then we get log of u as our antiderivative. And we're going to back substitute. So we go back to our x's. So back to our t's. We get this. And then, so this is our antiderivative in terms of t. And then to evaluate the integral, we just have to plug in 2 and plug in 1. Those were the limits of our original integral. So we plug in 2 and we plug in 1. And that gives us this value, which I think was, let's see. Let's see what our original statement gave us in Mathematica. T1, 2. Yeah, so it gave us the same thing. if you combined these logs, we get 3/2 is our coefficient. And since we're subtracting, this 5 goes into the denominator of our argument. So we can do this by hand, even though we can also do this with Mathematica. That was a fun problem. That was the first integration problem that we've done in the live stream. That's cool. Well, it looks like it's time to wrap up the show. So I hope all of you are enjoying learning calculus. I hope that this was helpful to you. I'm enjoying making these live streams. I hope that you're enjoying watching them. So I hope you all have a great day, and goodbye.